Hello, my name is Khalil Guy, and today I'll be presenting my talk on optimizing quantum circuit layout using reinforcement learning. This research was supervised by Dr. Gabriel Perdue in the Fermi Quantum Institute at Fermilab. And so what is quantum computing? Quantum computing is the type of computing which leverages quantum mechanical properties in order to perform computations. And this type of computing has been seen to offer a significant speed up for certain algorithms over classical computers. And this is very important because as we move towards certain problems, quantum computing has been seen as key in solving very difficult problems in areas such as chemistry and physics, as well as showing unique applications in areas such as finance and cybersecurity, just to name a few. And the main way by which quantum computing takes place is through a quantum circuit, where a quantum circuit is a model for quantum computation using gates, which act on quantum bits or qubits, where the qubits are outlined in the red block and the gates are outlined in the purple block. And you can implement a simple circuit like this on your very own device using one of the several available quantum computing frameworks such as IBM's Qiskit and Google Cirq. But it's very important to know that this can only be done for small numbers of qubits. But as we push towards a regime where quantum computers consistently outperform classical computers, we need more qubits. And this will be essential. And this is where the quantum computer chip comes in, which is one of the principal components in a quantum computer, as it allows us to physically realize quantum circuits. But there's a couple of problems with quantum computing. And this is mainly seen in that the devices are imperfect or noisy, where interactions with the environment can affect the states on the qubits. And you may not get a particular state that you want depending on the noise in the environment. And so while there are several ways of mitigating this noise, the main way that we look at is through optimizing the circuit layout. Where the goal of this is to translate our virtual circuit to the physical hardware in a way where the circuit or the states on the qubits are affected the least by noise. And so while there have been some exact algorithms that do the circuit optimization, they don't scale very well, meaning that as you increase either the size of the circuit or the size of the hardware, the algorithms can become very slow or very inefficient. However, heuristic algorithms or algorithms which are able to learn by themselves have been shown to scale much better. So this is why we want to look at reinforcement learning, which is a type of heuristic based in machine learning. And we want to explore the implementation and performance of a reinforcement learning model. And that is precisely the objective of our research. We want to implement a reinforcement learning model which builds optimized quantum circuits based on observed noise characteristics. And this is going to be done for a simple class of circuits. What we do is there are two main components to an RL model, the first being the agent and the other being the environment. And what we focus on is the first thing that we need to focus on is to create the environment, which is what we do. And we build this environment using OpenAI Gym, in which an RL agent can make choices that will build a class of simple circuits on some hardware. And the agent circuit that it creates is represented in the bottom right diagram. And so as we move forward, we actually want to train an RL algorithm to build these circuits. And we want to do this with the following questions in mind. What is the base state representation of the environment? What is the RL algorithm which will perform the best in the proposed environment? And also, how do we generalize this environment to more classes of circuits? And we believe that with reinforcement learning, we will be able to propose another viable method of quantum circuit optimization. Thank you.